In this video, we're going to look at the common emitter configuration. We're going to be deriving the gain, but we're going to start with a simple configuration, and then as the video progresses, we're going to start adding complexities. You'll see what I mean. Let's go ahead and get started. It's important that the bipolar transistor be biased in the forward active mode. That means that the voltage here at the collector needs to be higher than the voltage at the base, and the voltage at the base needs to be higher than the voltage down there at the emitter. This letter H configuration formed by resistors R1, R2, RC, and RE allows that voltage progression from high to low as we look down from top to bottom. In order to calculate the gain, we're going to start off by kind of ignoring the left side and the right sides of these circuits. You see that we have capacitors here, and those are basically to allow the signals to be added. We're ultimately going to add this AC signal from the source to the DC signal from the biasing network, and then here at the output side, we're just going to collect the AC signal and discard the DC signal. To start off with, though, we're just going to be ignoring those AC signals. Let's start off by calculating the DC voltage at the base. I'm going to assume that we have a certain voltage here at the power supply given by V sub P, and resistors R1 and R2 form a voltage divider. I'm going to neglect the current into the base itself. The voltage at the base is then just a simple divider set up by resistors R1 and R2. Let's now find the DC voltage at the emitter. Now, the voltage across the base emitter junction is just a forward bias diode. If it's a silicon transistor, that voltage drop is going to be about 0.7 volts. Therefore, the voltage at the emitter should just be exactly what the voltage at the base is, dropped by 0.7 volts. So let's go ahead and write it down. Now that we know the voltage at the emitter, let's find the emitter current by applying Ohm's law across the emitter resistor R sub E. I just need to take the voltage that I've just written down and divide it by R sub E. This is the current that we've just found, and I am going to assume that the base current is small. And if the base current is small and the beta of the transistor is reasonably large, then the current up here at the collector should almost equal the current down at the emitter. In other words, I'm just going to assume that these two currents are identical. If I assume that the current up here at the collector is the same as the current at the emitter, then I can write the voltage here at the collector by applying Ohm's law across resistor R sub C. Let's go ahead and write down what the voltage at the collector should be. Well, the voltage is definitely going to be less than the power supply voltage, and it's just going to be the emitter current times R sub C below that power supply voltage. So we just need to multiply what I've just written for the emitter current by R sub C. Now we're done. We have an expression for the collector voltage. Now the question is, how is this voltage going to change if I add in my AC signal or my source voltage? Let's go ahead and see how it changes, but I'm going to neglect the effect of the source resistor R sub S. In other words, I'm going to assume for the time being that this resistor R sub S is small. If it's small, then there won't be any voltage drop across it. The voltage here going across the capacitor will just be my AC voltage V sub S. How is the presence of the AC source going to affect my base voltage? Well, they're just going to add. I'm going to label it V sub B for the time being because later we'll incorporate that resistor R sub S into our analysis. We now have two parts of this expression for the voltage at the base. We have a DC term and an AC term. Our voltage at the emitter is also going to be modified by that AC term at the base. It's just going to add to it. Let me go ahead and propagate that AC voltage through the rest of the expressions. It's going to show up in the emitter current, and then it's also going to show up in the collector voltage too. Now, for the time being, I'm going to ignore the fact that we have a load resistor attached to the circuit. In other words, I'm going to assume that this load resistor R sub L is large. When it's large, I'm effectively neglecting the fact that there's some current through it. Very little current will flow through that resistor if it's large. If the resistor is large, then my expression for the collector voltage is almost accurate. Now, what's going to happen across this capacitor here attached to the collector? My goal here is to find the load voltage. Let's label it V sub L. You see, the capacitor at the collector is going to block all of the DC components of the collector voltage. Only the AC part is going to get through that capacitor to the load. So let's look at our expression for the collector voltage and ask ourselves, what's the AC part of this signal? Well, V sub P is a DC term. This is also a DC term. This is also a DC term. The only term that's left is V sub B times the ratio of those two resistors. So let's just write it down. We now have an expression for the gain. The gain of this circuit, if we have a small source impedance and we have a large load, is just the ratio of the collector resistor to the emitter resistor. It's negative RC over R sub E. Now, there were some assumptions that went into that calculation. I assumed that the transistor was correctly biased in the forward active mode, and I assumed that the source impedance was small and the load impedance was large. But those are actually normally reasonably valid assumptions. Let's now go ahead and look at an example and calculate the gain by inspection. By inspection, I can see that the gain of this circuit is going to be approximately -1. Why is that? Well, I see that the collector resistor is 1 kilo ohm, the emitter resistor is 1 kilo ohm, and it's common emitter amplifier. Therefore, the gain should be -1. Now, that calculation relies on R sub S being small. Is it small here? Well, 10 ohms actually is pretty small when we compare it to the 10 kilo ohms here and here. Now, is our load resistor large? Yes, it is. A mega ohms is 1,000 times larger than our output impedance here of 1 kilo ohm. Our calculation of the gain also relies on the transistor being in the forward active mode. Is the transistor in the forward active mode? Well, to know, we'll need to kind of look at the circuit and decide, do the voltages properly progress from high to low as we look down the circuit? It's going to happen here in this circuit, but let's go ahead and calculate things out just to be sure. First of all, our base voltage is just 5 volts. It's a voltage divider from the 10 volt power supply across these two 10 kilo ohm resistors. What's our emitter voltage? Well, it's just going to be about 0.7 volts below our base voltage, 4.3 volts. What's our emitter current now? Well, it's going to be 4.3 divided by our emitter resistance, which is just 1 kilo ohm. We'll now assume that our collector current is nearly equal to our emitter current, and we'll find the voltage at the collector. It's going to be 10 minus my emitter current times my collector resistor, 5.7 volts. Let's look at our voltages. We have 5.7 volts up here at the collector, we have 5 volts at the base, and we have 4.3 volts down here at the emitter. The voltages are properly progressing from high to low. Therefore, this transistor ought to be in the forward active mode. It's not saturated and it's not cut off. Let's now calculate whether the base current is negligible or not. You see, my calculation of 5 volts here at the base relies on me being able to neglect that base current. Was the base current actually negligible relative to the current down through these 10 kilo ohm resistors? Let's find out. Well, my base current is about 1/100th of my emitter or collector current. And here, my emitter current was 4.3 milliamps. So 1 divided by beta times 4.3 milliamps is 0.043 milliamps. We need to compare it to the current down through this 10 kilo ohm resistor. Let me label it I. I is just my base voltage divided by 10 kilo ohms. We find that the current down through that 10 kilo ohm resistor is 0.5 milliamp. Compared to our base current, 0.0043 milliamps, we can conclude that the base current is basically negligible. That means that all of the assumptions that went into my calculation for the gain were reasonable. Therefore, I conclude that the gain of this entire amplifier is approximately -1. Now look at how easy it was. By inspection, all I had to do was to look at the resistor at the collector and divide it by the resistor at the emitter. That's the gain of the common emitter amplifier. Now, we did have some complications. What if the source resistance is not negligible? What if the load resistance is not so large? In just a moment, we're going to go back and see how those complications would affect our expression for the gain. But before we do that, let's look at our capacitors. We know that these capacitors form high-pass filters. If the frequency is high, it'll go right through this amplifier. But what happens if the capacitors are too small? If these capacitors are too small, then our frequency might be cut off. In example 2, we're going to assume that the signal is an audio signal. Are the capacitors large enough? Let's see what happens. Let's look at the resistance going into that amplifier and label it Rn. If you've seen my previous video on one-pole filters, you'll immediately recognize this as a one-pole high-pass filter. What's the corner frequency of that filter? That's what we're going to calculate right now. If we plug in R sub n, which is about 5 kiloohms, 10K in parallel with 10K, and a C of 100 nanofarads, then we'll calculate that the corner frequency here is about 318 hertz. How about over here at our load? We have the same configuration over here. It's a one-pole high-pass filter. The resistance here is a lot larger, so the corner frequency works out to be 1.59 hertz. These are high-pass filters, so higher frequencies can get through the capacitors. The output capacitor is just fine because the frequency is so low, any audio signal can pretty much get through it. But how about here at the input side? 318 hertz, that's somewhere in the middle of the audio spectrum, so the low frequencies are definitely going to be attenuated by that first capacitor. The answer to this problem is that this capacitor here at the output side is large enough, but the capacitor here at the input side is not large enough. What would be a more reasonable value for that first capacitor? Well, let's see. If we used a 1 microfarad, then that would put our corner frequency at 31.8 hertz. Probably okay, but if it were me, I would make it even 10 times larger than that. 10 microfarads would put our corner frequency at 3.18 hertz. Perfect. Now, let's go back to our derivation for the gain and see what effect the input and output resistors will have on that expression. Now, our previous expression for the gain was just minus RC divided by R sub E. But we know there's going to be a voltage divider set up here at the input side and some kind of a current divider at the output side. Let me show you what I mean by drawing the small signal equivalent circuit. In other words, I'm going to redraw the circuit that we already have, but from the perspective of the small signal going through it. For example, if our capacitor here is large enough, the AC signal is going to go right through it, so it's like the capacitor is not even there. It's not going to see it, is it? So I'm not going to include that capacitor in our circuit. Here's our input impedance. It's just R1 in parallel with R2 because R1 is connected to an AC ground and R2 is connected to a real ground. This is our base voltage. You can now see what effect R sub S would have on the circuit. If R sub S is too large, then the base voltage is going to be smaller than the source voltage, isn't it? We have a voltage divider set up right here at the input side. I can even write the expression for V sub B in terms of V sub S. Again, it's just a simple voltage divider. Now what happens here at the output side of the circuit? I'm going to label the current going down through that transistor with I sub C, the collector current. Now before, I neglected the current through the load resistor because I assumed that resistor was really big. But now I'm not going to neglect it. I'm going to assume that the load resistor could be anything. When I assume that the load resistor can be anything, it means that there might be some current going through it. There definitely won't be any DC current going through it, but from the AC circuit's perspective, we could have AC current going through the load resistor. Let's continue to draw our AC equivalent circuit by representing the collector of that transistor as a current source. The current source pulls current through the collector resistor R sub C, which is connected to an AC ground, and it also pulls AC current through our load resistor R sub L. We have a current divider here at the output. Let me go ahead and label our load voltage and call it V sub L. I could label it up here in our real circuit as well. What's our expression for the AC current I sub C? Well, we can just apply Ohm's law here. It's just V sub L divided by R sub C in parallel with R sub L, isn't it? We also know that our collector current, the AC portion of it anyway, is equal to the AC portion of the emitter current, and I can see what that is right over here on the left. Let's now rearrange this expression that I just found in order to find the load voltage in terms of the base voltage. This is our basic expression for the gain without considering the input side of the circuit. It's just all of the resistors attached to the collector divided by the resistor connected to the emitter. There's another way to write this too. We could think of the load resistor R sub L as setting up a voltage divider at the output. I could think of the output impedance of this amplifier as just being R sub C. Now, of course, it's R sub C in parallel with the resistance looking down into the collector, but that's typically a really big number, so we're just going to neglect it. We're always going to neglect it, in fact. I can now model our entire common emitter amplifier by 3 different circuit segments: an input voltage divider, a gain section, and an output voltage divider. In order to find the gain of a common emitter amplifier, you can just remember resistance at the collector divided by resistance at the emitter. And then the input and output sides you can find by inspection from the circuit. Let's use our little model now to find a complete expression for the voltage gain of this common emitter amplifier. We have our input voltage divider, we have our gain segment, and now we have our output voltage divider. You can see from this expression that if the source resistance is small, then we can neglect the first term. And you can also see that if the output impedance is small relative to our load, then we can neglect the output side as well. Now that we have our expression for the voltage gain, let's look at our circuit and figure out what we might do if we want to make as large a gain as possible. After all, we're making an amplifier here, so we probably want a high gain. Well, we can basically use a large collector resistor, and we can use a small emitter resistor. In other words, we'll make the ratio R sub C divided by R sub E as large as possible. But what's going to happen if we make resistor R sub C too large? Well, look at our expression for the voltage at the collector over here on the left. You see, the voltage at the collector gets lower and lower the larger we make R sub C. Now, if the collector voltage gets too low, it might drop below our base voltage and start to saturate the transistor. That means that there are practical limitations on how big R sub C can be. So we're not going to make the gain too large just by increasing R sub C. Now, what about on the emitter side? What happens if we make the emitter resistor too small? Well, the smaller we make R sub E, the larger the current through the emitter becomes. The larger the emitter current, the larger the base current, and the base current starts to become non-negligible. So now we're in a conundrum. We have an expression for the gain, and we know how we ought to increase it, but we are really limited by how much we can increase it. We can't make R sub C too large, or we'll saturate the transistor, and we can't make R sub E too small, or the gain may be dependent on the base current. We don't want either of those two things. Here's the solution. We're going to use an emitter bypass. This is going to change the AC gain without screwing up our DC bias conditions. Imagine for a moment that this branch is not attached to the circuit. we'll come up with a certain expression for the base voltage, a certain expression for the emitter voltage, and a certain expression for the collector voltage. Now imagine I attach that branch, the one here circled in red. Are any of those voltages going to change? Well, the DC voltages will certainly not change because this is just a capacitor, right? DC voltages can't go through it. So I've just shown you that this branch added to the circuit doesn't change anything related to our DC biasing, but it will change the AC gain. Without that branch attached, our gain is just going to be R sub C divided by R sub E. But you might start to see what could happen with the branch there. The DC signal is not going to see it, but the AC signal will see that branch. The AC signal, in other words, is going to see a different emitter resistor. That new gain is going to be minus RC divided by these two resistors in parallel with one another. We now have a way to tune the AC gain without screwing up our DC bias conditions. This is the way to do it. This is how you design common emitter amplifiers. Let's draw an AC equivalent circuit and then write down the full expression for the gain. First, we have our input side, and we're going to come up with an expression for the input impedance. It's just going to be R1 in parallel with R2. Well, we do also have a third branch going into the base of that transistor, but we'll look at that later. We're just going to assume that it's large for now. Here we have our gain branch. Let me label it A. Now we have our output branch, and the output impedance here is just R sub C. What's our overall expression for the gain? Well, we have our input side, then we have our gain A, and then we have our output side. There are a lot of variables in the expression, but if you can remember how to draw the AC equivalent circuit, and you just remember that the gain is the collector resistance divided by the emitter resistance, then it's not too difficult to get the hang of it. Let's now work some examples and apply what we've just learned. Let's estimate the AC gain for this circuit. Well, first of all, I note that we've got a 1 kilo ohm resistor here, and we've got something less than 1 kilo ohm down here. So the gain of this circuit is going to be more than 1, or the absolute value of the gain is going to be more than 1. It's common emitter configuration, so it's definitely going to be inverting. We don't have too much of a voltage divider at the input side, but we do have a bit of a voltage divider at the output side. I guess that the gain of this circuit might be around -1. Let's see how it turns out. Since the frequency is at 1 megahertz, and these are pretty large capacitors, I can be reasonably sure that that radio frequency signal is just going to zoom right through those capacitors. The filter is not going to matter here, so I'm pretty much just going to ignore those capacitors. Our input impedance is around 5 kilo ohms. Again, I'm neglecting the resistance looking into the base of that transistor. Our output impedance is around 1 kilo ohm, and we always neglect the large impedance looking down into the collector of a transistor. We now have everything we need in order to calculate the gain. Let's do our input voltage divider first. We have our input impedance dividing across that 100 ohm source impedance. Now we have our gain segment, which is 1 kilo ohm divided by these two resistors in parallel with one another. And now we have our output voltage divider. It's our load resistor and our collector resistor that create the voltage divider here. If we plug in numbers, we find that the input divider gives us 0.98. Not too serious, right? Here for our gain segment, we have -3, and our output voltage divider gives us about 0.44. Overall, our voltage gain here is about -1.3. We've just seen that if we bypass the emitter resistor, we can increase the gain. What if I fully bypass it? The AC signal is now not going to see any resistor down here at all for the emitter, so is my gain going to go to infinity? Well, not really. I need to show you how to deal with this situation. Let's first draw our AC equivalent circuit. I'm going to label my base voltage and my input impedance. After the input segment comes the gain segment. I'm just going to label it A for the time being. Now we have our output segment. The output resistance is just R sub C. Previously, we had a resistor here. We called it RE1. The gain of the circuit was just RC divided by RE in parallel with RE1. But here, RE1 is 0. So does it mean that the gain is RC divided by 0? That would give you an infinite gain, and that's not going to happen because, in fact, there is a little bit of resistance due to the junction inside of the transistor. In other words, we've got a little resistor right here, and I'm going to label it little RE. Normally, it's too small to be of any importance, but here it's going to matter, obviously, because it's the only resistor we have. It's in series with resistor RE, which has been bypassed by the capacitor. So let's write down a new expression for the gain. Here it's just going to be R sub E. Now the question is, how do we find it? How do we know what this little resistance is? In order to find it, you first need to find what the DC emitter current is. I'll call it I sub E here. You're going to have to just remember this formula. It's Boltzmann's constant times the temperature in Kelvin divided by the DC emitter current. At room temperature, this constant in the numerator works out to about 26 millivolts. If you express the DC emitter current in milliamps, then you can just remember the formula 26 divided by I sub E in milliamps. That'll give you the emitter resistance R sub E. For example, if your emitter resistance is 26 milliamps, then your R sub E is just 1 ohm. These numbers do tend to be really small. If you've got an R sub E down here that's not bypassed, then it's pointless to include the little R sub E in your calculations. Let's now work an example and use what we've just learned. We see that the emitter resistance is fully bypassed by the 10 microfarad capacitor. So let's start off by calculating little R sub E. Well, we have a 20 volt power supply and two 10 kilo ohm resistors, so my base voltage is going to be about 10 volts. My emitter voltage is going to be about 0.7 below that. The DC emitter current all flows through that 1 kilo ohm resistor, so it's going to be 9.3 milliamps. I now have everything I need in order to calculate little R sub E. 26 divided by 9.3. It works out to about 2.8 ohms. That's pretty small resistance value, so I expect we're going to have a pretty good gain from this particular amplifier. Let's label R sub in and R sub out, and now I'm going to draw my AC equivalent circuit. My voltage gain is going to be 1 kilo ohm divided by R sub E. That ratio is 357, so the gain segment is going to give us a pretty big number here. My output impedance is 1 kilo ohm, and then finally we have a load of 800 ohms. My gain consists of an input voltage divider, then a gain segment, and then an output voltage divider. Let's estimate our input impedance as being 10 kilo ohms going to the AC ground in parallel with 10 kilo ohms going down to the other AC ground. That's going to give us 5 kilo ohms. I'm going to show you in a minute, though, that that number is not really correct anymore because we've bypassed the emitter resistor. Nonetheless, we still get a reasonably accurate value for the gain. If I plug in Rn equals 5 kilo ohms to this expression, then I'll determine that the gain is minus 156. I now want to show you how we can estimate the base input impedance a little bit more accurately, and we're going to have to do that when we bypass the emitter resistor. Previously, we assumed that this resistance was simply too large and we just ignored it. In some textbooks, they like to call that resistance R sub pi, and the label pi comes from something called the pi model of the transistor. Here, it's just a label. I'm going to call the resistance looking into that base R pi. If I label R sub in as the input impedance to the amplifier, I can just write that Rn is R1 in parallel with R2 in parallel with R pi. Now, what does the transistor look like from the perspective of an AC signal? Well, we have our little resistor R sub E, and then it's connected to an AC ground. So how does R sub E look if we're labeling it from the base? It turns out that in order to find R pi, you just need to multiply the R sub E times beta. Let me write that down. R sub pi equals beta R sub E. Now, why is that? Why does the resistor somehow look larger from the base side than it does from the emitter side? One way to think about it is like this. On the base side, we have small currents. On the emitter side, though, we have large currents. Remember, the base current is a small number, but the emitter current is approximately beta times the base current. Therefore, the currents at the emitter are about 100 times larger than the currents at the base. How about the voltages, though? Is the AC voltage at the base larger or smaller than the AC voltage at the emitter? Well, they're typically the same number. It's just a forward bias junction, so when the base moves up, the emitter moves up, and likewise when they move down. These AC signals just move together. So the voltages are pretty much the same. Now think about Ohm's law. If you have the same voltage, but a small current and a large current, then the resistor is going to have the opposite relationship. The base side sees large resistances, and the emitter side sees small resistances. This is called impedance reflection. In the next video, we're going to look at impedance reflection in more detail so you can see how to apply this in transistor circuits in general. But for now, I hope you can appreciate that the emitter resistance R sub E is going to look like a bigger resistance as seen from the base. The reason why the emitter resistance looks large when you view it from the base is because the base doesn't contribute very much current. It's only contributing about 1/100th of the necessary current to maintain the emitter voltage. Since it doesn't have to work very hard, it thinks that there's a large resistance there, beta R sub E. We'll look at this in the next video in more detail, but for now, let's go back and correct our gain calculation in the last example. Let's now come up with a more accurate estimate for my input impedance. We still have our two 10 kilo ohm resistors, just like we did before, but now we have this new branch, beta RE. We can estimate beta as being around 100, and we know that R sub E is about 2.8 ohms. That works out to about 1795 ohms. Before, we said that it was about 5,000 ohms, so that wasn't really a very accurate estimate, was it? Nonetheless, both of these numbers are large relative to my R sub S, so it turns out not to really affect the gain calculation too much in this example. If I plug in the more accurate estimate for my input impedance, I wind up getting around minus 150 for the final version of the gain. You see, it's not really all that different from 156, but it is slightly more accurate, and it shows you at least how to handle the resistance looking into the base of a transistor. In the next video, again, we're going to look at this impedance reflection in a little bit more detail.